The morning of March 3rd, 1944. Wright Field, Dayton, Ohio. The temperature is 18 degrees Fahrenheit, and the sky is that particular shade of grey that promises more snow before noon. On the frozen tarmac, 3 fighter aircraft sit in a neat line like students waiting for an exam they didn't study for. A P-38J Lightning, a P-47D Thunderbolt, and a P-51B Mustang. They're about to be fed fuel that shouldn't exist. Fuel that violates every economic principle the petroleum industry has spent 2 decades establishing. Fuel that costs more per gallon than most Americans earn in a day. And if the numbers from this morning's test flights are correct, fuel that's going to make every Luftwaffe fighter in Europe obsolete by summer. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crew chiefs are nervous. Not because the aircraft are experimental. They're standard production models, pulled from the line with maybe 50 hours on their engines. Not because the test pilots are inexperienced. These are Wright Field's best, men who've logged thousands of hours and can feel a 2-mile-per-hour difference in airspeed through their fingertips. They're nervous because of what's in the fuel trucks: 150 octane aviation gasoline, grade 104/150 in the official designation, 4.6 cubic centimeters of tetraethyl lead per gallon, mixed with aromatic compounds that smell like concentrated industrial death. The fuel is purple, literally purple, dyed that color so ground crews can't accidentally mix it with anything else, because if you pour this stuff into an engine that wasn't built for it, you might as well be pouring in battery acid. The test protocol is simple. Fly each aircraft through its performance envelope. Maximum speed runs at 5,000-foot intervals, from sea level, 35,000 feet. Rate of climb measurements. Time to altitude benchmarks. Then compare the results to the baseline data from the same aircraft running standard 100/130 octane fuel. The engineers expect improvements. Maybe 5 miles per hour. Maybe an extra 200 feet per minute in climb rate. Incremental gains that would look good in a technical report and might justify the fuel's astronomical production cost if you squinted at the spreadsheets in the right light. What they're about to get is something else entirely. To understand why 3 fighters sitting on a frozen runway in Ohio are about to rewrite air combat doctrine, you need to understand what Octane actually means. And you need to understand that the path to this moment started not in a laboratory or a military planning office, but in the mind of a barnstorming pilot who couldn't leave well enough alone. 1930. James Harold Doolittle, known to everyone as Jimmy, walks away from active duty in the United States Army Air Corps. He's 33 years old. He holds a doctorate in aeronautical engineering from MIT, the first such degree ever issued in the United States. He's set multiple speed records, won air races that made him famous from coast to coast, and pioneered instrument flying techniques that would make all-weather aviation possible. He's also completely convinced that the next war is coming and that America is going to lose it because of gasoline. The Shell Oil Company hires him as Aviation Department Manager. It's a prestigious position with a comfortable salary, and most men would treat it as a reward for an accomplished career. Doolittle treats it as a platform to fix a problem that nobody else recognizes exists. The problem is this: aircraft engines in 1930 are limited not by their mechanical design, but by their fuel. When you compress a mixture of air and gasoline inside a cylinder and then ignite it with a spark plug, you want that mixture to burn in a controlled manner. A smooth, powerful expansion of hot gases that pushes the piston down and turns the crankshaft. What you don't want is detonation. That's when the fuel-air mixture explodes prematurely, before the spark plug fires, or when it explodes in multiple locations simultaneously, instead of burning in a smooth wave from the spark plug outward. Detonation creates shock waves inside the cylinder. It sounds like someone hitting the engine block with a ball-peen hammer. Engineers call it knock, and it will destroy an engine in hours if you let it happen continuously. The higher you compress the fuel-air mixture before ignition, the more power you can extract from each explosion. Higher compression ratios mean more horsepower from the same size engine, which means faster aircraft or aircraft that can carry more weight. But higher compression also makes detonation more likely because you're squeezing that mixture harder before it ignites. This is where octane comes in. Octane is a measure of a fuel's resistance to detonation. The scale is built around two reference compounds. Pure isooctane, which resists knock extremely well, is assigned a rating of 100. Pure N-heptane, which detonates at the slightest provocation, is assigned a rating of 0. If your fuel has an octane rating of 87, it means it performs like a mixture of 87% isooctane and 13% N-heptane. In 1930, aviation gasoline has an octane rating between 70 and 80. Automotive gasoline is even worse, around 40 octane. Aircraft engines are designed to run on this fuel, which means they're designed with low compression ratios, which means they're producing far less power than their physical size suggests they should be capable of. Doolittle sees the trap clearly. Engine manufacturers won't design high-compression engines because there's no high-octane fuel available to run them. Oil companies won't invest in expensive refining processes to make high-octane fuel because there are no engines that need it. It's a perfect catch-22, and it's keeping American aviation stuck in a performance envelope that's about to become fatal. Because in Germany, Daimler-Benz and BMW are designing liquid-cooled V12 engines with fuel injection systems and sophisticated superchargers. These engines are already running on fuel with octane ratings in the high 80s, and they're producing power levels that American radial engines can't match. The Messerschmitt Bf 109, powered by a Daimler-Benz 601, is faster than anything in the American inventory. The gap is only going to widen. Doolittle starts lobbying Shell executives to invest in refining capacity for 100-octane gasoline. The initial reaction ranges from skeptical to openly dismissive. 100-octane fuel in 1934 costs approximately $30 per gallon. $30. When regular automotive gasoline sells for less than 20 cents. The economics are absurd. But Doolittle has both technical expertise and star power. He's famous. His name sells newspapers. And he's willing to put his own life on the line to prove his point. In 1932, flying a Guy B. Rone raceplane fueled by Shell's experimental high-octane gasoline, he sets a world landplane speed record of 296.287 miles per hour. He wins the Thompson Trophy race with an average speed over 250 miles per hour. He's demonstrating, in the most public way possible, that high-octane fuel delivers real performance gains, not theoretical improvements on paper, actual, measurable speed that crowds can see with their own eyes. Shell finally commits. In 1934, the company begins investing in refining equipment to produce 100-octane fuel at scale. It's an enormous gamble. The initial plant capacity produces fuel that still costs several dollars per gallon. There is no market. No aircraft exist that require it. Some Shell employees start calling the project Doolittle's $1 million blunder. But Doolittle has a plan for creating that market, and it involves convincing the United States Army to completely rewrite its fuel specifications. 1935. The Army Air Corps operates approximately 1,500 aircraft. Fewer than 50 of them can take advantage of 100-octane gasoline. The service's standard fuel specification calls for 87 octane. That's what the logistics system is built around. That's what the existing aircraft are designed to burn. Changing the standard means redesigning engines, modifying existing aircraft, rebuilding fuel storage and distribution systems across dozens of bases. It's a massive undertaking with no obvious justification. Doolittle, still nominally a reserve officer with the rank of major, starts testifying before Army procurement boards. He brings data. He brings performance charts. He brings engines that have been modified to run at higher compression ratios, demonstrating the power gains that higher octane enables. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. More importantly, he brings fear. He's been to Europe. He's toured the Luftwaffe's facilities, seen their aircraft, talked to their pilots, And he's telling anyone who will listen that American military aviation is falling behind, not in pilot skill, not in aircraft design, in the fundamental chemistry of the fuel feeding the engines. In July 1934, the Army begins experimental testing with 100-octane fuel. The results are immediate and undeniable. Engines that produced 600 horsepower on 87-octane are suddenly producing 750 or 800 horsepower on 100-octane. The same engines, the same airframes, just different fuel allowing higher manifold pressures without detonation. In January 1936, Major General Henry Hap Arnold becomes Assistant Chief of the Air Corps for Procurement. Arnold understands what Doolittle has been saying. In 1937, the Army establishes 100-octane as its new standard fuel specification for combat aircraft. The Navy follows. The market Doolittle needed finally exists. Shell scales up production. Other oil companies, seeing military contracts and Army orders, start building their own refining capacity. By 1939, 100-octane aviation gasoline is being produced in thousands of gallons per day. The price has dropped to around 35 cents per gallon, still more expensive than automotive fuel, but no longer absurd. And then two things happen that prove Doolittle was right. First, war breaks out in Europe. Second, it becomes immediately clear that fuel octane is as much a weapon as bullets and bombs. May 1940. The Battle of France. Royal Air Force Hurricane and Spitfire squadrons, flying from bases in France and England, engage Luftwaffe. Messerschmitt Bf. 109s over the evacuation at Dunkirk. The early results are grim. The German fighters are faster, 20 to 30 miles per hour faster in level flight. They can climb higher. They can disengage from combat at will by simply accelerating away. If a Messerschmitt pilot gets into trouble, he doesn't have to outfight the British pilot. He just has to outrun him. And he can, every time. The Spitfire and Hurricane are good designs. The Rolls-Royce Merlin engine is a sophisticated piece of engineering, with a two-stage supercharger and intercooling. But in early 1940, these aircraft are running on 87-octane fuel. The engines are rated for 6¼ pounds of manifold pressure boost. The power output is good, but it's not enough. The RAF's Air Ministry has been stockpiling 100-octane gasoline since June 1939. They got the fuel from American refineries, from Shell and Standard Oil, shipped across the Atlantic by tanker. But the aircraft engines haven't been modified to use it. Running 100-octane fuel through an engine designed for 87-octane gives you almost no benefit, because the engine still can't compress the mixture hard enough to take advantage of the fuel's anti-knock properties. In March 1940, with France collapsing and Britain facing the very real possibility of invasion, the RAF makes an emergency modification to its frontline fighters. The Merlin engines get shrouded cylinder heads and revised fuel systems that allow them to run at 12 pounds of manifold pressure instead of 6¼ twice the boost, on 100-octane fuel. The performance gain is staggering. Hurricanes and Spitfires suddenly gain 25 to 34 miles per hour in top speed. Rate of climb increases by 500 to 1,000 feet per minute depending on altitude. The critical altitude where the engines can still produce maximum power increases dramatically. By July 1940, when the Battle of Britain begins in earnest, the Luftwaffe's performance advantage has evaporated. Messerschmitt pilots who spent May and June confidently running away from British fighters are now discovering that the Spitfires can keep up, can catch them, can kill them. German intelligence eventually figures out what changed. Captured RAF documents refer to the new fuel. The Luftwaffe starts calling it der Treibstoff, the fuel, like it's some kind of secret weapon, because that's exactly what it is. The 100-octane fuel doesn't just increase speed. It increases options. A Spitfire pilot can now choose to engage or disengage. He can chase a Messerschmitt that's trying to escape. He can climb to intercept bombers at higher altitudes. The entire tactical situation shifts, and it shifts because of chemistry, not because of airframes or guns. Doolittle's gamble, the million-dollar blunder that Shell executives mocked in 1934, helps save Britain. This is not hyperbole. Multiple military historians have argued that without the 100-octane fuel reserves Britain had built up, the RAF would have lost air superiority during the Battle of Britain, which would have made a German invasion plausible, which could have knocked Britain out of the war. All because one pilot with an engineering degree understood that fuel was a weapon system and was willing to spend 6 years convincing people who thought he was crazy. But 100-octane is just the beginning, because by 1943, American engineers are looking at combat reports from Europe and the Pacific and realizing that 100-octane isn't enough, not against the aircraft Germany is now fielding, not for the missions the Army Air Forces is trying to fly. The heavy bombers, B-17s and B-24s, are flying deep into Germany in daylight raids. The fighter escorts, P-38s and P-47s, have range limitations. They can only go so far before they have to turn back, and the Luftwaffe, understanding this, waits until the escorts leave and then swarms the bomber formations with everything they have. The P-51 Mustang, with its Rolls-Royce Merlin engine and enormous internal fuel capacity, can theoretically escort bombers all the way to Berlin and back. But theoretically isn't the same as actually. The performance margins are tight. If a Mustang pilot has to run at full power for an extended period, fighting off German interceptors, he might not have enough fuel to make it home. What the Army needs is more performance from the same engines, more speed, more climb rate, better altitude performance. And there's only one way to get it: better fuel. The research starts in Britain in 1942. The Royal Aircraft Establishment at Farnborough begins testing fuel formulations that push beyond 100 octane. They're working with oil companies, primarily Shell and Standard Oil, experimenting with different blends of aromatic compounds and different concentrations of tetraethyl lead. The challenge is complex. You can't just add more lead and call it a day. Too much lead fouls spark plugs, it creates deposits on cylinder walls, it reduces the life of the engine, and lead is toxic. Horrifically toxic. Ground crews handling high lead fuels suffer from headaches, nausea, tremors. The stuff is poison, and everyone knows it, but it's the only anti-knock additive that works at the concentrations needed. The aromatics are almost as bad. Benzene, xylene, xylene, these are compounds that smell sweet, almost pleasant, right until they give you liver damage or leukemia. The chemists working with these fuels wear respirators and work in ventilated facilities, and even then, some of them get sick. But the performance gains are impossible to ignore. By late 1943, British test pilots are flying Spitfires and Tempests on experimental fuel blends, rated at 150 performance number, not 150 octane. You can't have octane ratings above 100 because the scale ends at pure isooctane. Instead, engineers use performance number, which measures how much better than isooctane the fuel performs. A fuel with a lean mixture performance number of 110 performs 10% better than pure isooctane. A fuel rated at 150 performs 50% better. The power gains these fuels enable are extraordinary. 25 to 30% increases in maximum horsepower, speed increases of 20 to 30 miles per hour, climb rates that jump by 500 feet per minute or more. The problem is production. Making this fuel is expensive. It requires sophisticated catalytic cracking processes. It requires rare additives. It requires quality control that exceeds anything the petroleum industry has ever attempted. A bad batch of this fuel won't just reduce performance. It will destroy engines in flight, potentially killing pilots. In the United States, the Army Air Forces Material Command starts receiving reports about the British fuel experiments. The chemists at Wright Field look at the data and start asking questions. If the British can make 150-grade fuel, can American refineries do the same? And if they can, what would it do to American fighter performance? In January 1944, Wright Field obtains several hundred gallons of experimental fuel designated grade 104/150. 104 is the lean mixture performance number. 150 is the rich mixture performance number. The fuel is formulated by blending alkylate base stock with specific ratios of aromatic compounds and 4.6 cubic centimeters of tetraethyl lead per gallon. It's purple, literally purple, because the Army wants to make absolutely sure nobody accidentally puts this stuff in the wrong aircraft. The dye is there to prevent mistakes that could be fatal. The test plan is straightforward. Take 3 fighter aircraft representing the 3 main types in service: P-38 for the twin-engine, turbocharged category, P-47 for the single-engine, radial, turbocharged category, P-51 for the single-engine, liquid-cooled, supercharged category. Run baseline performance tests with standard 100/130 octane fuel, then run the same tests with grade 104/150. Compare the numbers. See if the performance gains justify the costs. Nobody expects what they find. The P-38J goes up first, Lockheed's twin-boom fighter, powered by 2 Allison V-17 1089 engines with turbochargers. On standard 100/130 fuel, the engines are limited to 60 inches of manifold pressure. That's the maximum boost the engineers consider safe, without risking detonation. The test pilot, whose name appears in the official report only as Captain M, fills the tanks with grade 104/150 and climbs into the cockpit. The ground crew chief hands him a clipboard with the test protocol. Speed runs at sea level, 5,000 feet, 10,000, 15,000, 20,000, 25,000, 30,000, and 35,000 feet. Time to altitude measurements at 5,000-foot intervals. Rate of climb at each test altitude. The engines start with that distinctive Allison sound, a smooth mechanical growl that vibrates through the airframe. Captain M taxis to the runway, runs through his pre-flight checks, and advances the throttles. The P-38 lifts off and climbs into the grey Ohio sky. At 5,000 feet, he levels off and starts his first speed run. He advances the throttles to full military power. The manifold pressure gauges climb, 50 inches, 55, 60. Then, because the fuel can handle it, he keeps pushing, 65 inches, 70 inches. Manifold pressures that would have caused catastrophic detonation on standard fuel. The engines respond like they've been released from bondage. The airspeed indicator needle swings past numbers that Captain M has never seen before in level flight. He makes notes on his kneeboard, checks his instruments 3 times to make sure he's reading them correctly. Then he climbs to 10,000 feet and does it again. When he lands an hour and 20 minutes later, the ground crew can tell something unusual happened just by watching his face as he climbs out of the cockpit. He's not excited. He's not grinning. He looks like someone who just witnessed something that doesn't quite make sense. The engineering team pulls the flight recorder data. They run the numbers twice, then a third time. The P-38J, on grade 104/150 fuel, is 20 to 25 miles per hour faster than the same aircraft on standard fuel. At every altitude tested, the rate of climb has increased by 500 feet per minute. The time to reach 20,000 feet has dropped from 8 minutes to 6.5. These aren't incremental improvements. These are game-changing numbers. This is the performance difference between losing a dogfight and winning it, between catching an enemy aircraft and watching it escape, between surviving a mission and not coming home. The P-47D goes up next, Republic's massive radial-engined fighter, powered by a Pratt & Whitney R-2863. The Thunderbolt is a brute, heavily armed, heavily armoured, capable of absorbing punishment that would destroy lighter aircraft, but it's also heavy, and speed has never been its strongest attribute. The test pilot runs the same protocol, standard fuel baseline, then grade 104/150. The Army decides to keep the P-47's maximum manifold pressure at 65 inches, even with the better fuel. The R-2800 is already pushing the limits of what an air-cooled radial can safely do. Going higher risks thermal problems that no amount of octane can solve. But even at 65 inches, the performance gains are remarkable. The P-47 is, on average, 19 miles per hour faster from sea level to 35,000 feet. The climb rate increases by 410 feet per minute. It's not as dramatic as the P-38's gains, but it's still substantial, still enough to matter in combat. Then comes the P-51B, North American's Mustang, powered by the Packard-built Rolls-Royce V-1657 Merlin. This is the aircraft the Army is betting on for long-range bomber escort. This is the fighter that's supposed to go to Berlin and back. If any aircraft is going to benefit from better fuel, it should be this one. The initial tests use a P-51B equipped with the V-1653 engine. Standard fuel baseline runs produce numbers consistent with the manufacturer's specifications. Maximum speed 437 miles per hour at 25,000 feet. Time to 20,000 feet approximately 7 minutes. Good performance, but not exceptional. Then they switch to grade 104/150 and advance the manifold pressure from 61 inches to 75 inches. Pressures that would have been considered dangerously high just 2 years earlier. Pressures that are only possible because the fuel's anti-knock properties are so advanced. The Mustang transforms. Maximum speed jumps to 447 miles per hour, 10 miles per hour faster. But more importantly, the aircraft maintains that speed across a wider altitude range. The power curve flattens out. At low altitudes, the gains are even more dramatic. At 10,000 feet, the Mustang is picking up 15 to 20 miles per hour. But there's a problem. Midway through the test series, the V-1653 engine starts showing signs of carburetor issues. Nothing catastrophic, but enough to raise concerns about data validity. The engineers make a decision that's either inspired or desperate. They pull the 1653 and install a V-1657 engine instead. The 1657 is a newer variant with slightly different supercharger gear ratios. It's optimized for different critical altitudes. Designed based on combat reports suggesting most air-to-air fighting over Europe happens between 15,000 and 25,000 feet, not at the higher altitudes the 1653 was designed for. They run the tests again, and this is where the numbers become almost unbelievable. The P-51B with the V-1657, running on grade 104/150 fuel at 75 inches of manifold pressure, is 20 miles per hour faster than the same aircraft with the 1653 engine, not 20 miles per hour faster than the baseline, 20 miles per hour faster than the version they just tested with the better fuel. The climb rate increases by 580 feet per minute at 20,000 feet. The time to altitude drops across the board. The aircraft's performance envelope expands in every measurable dimension. The test engineers write up their report with language that's unusually strong for a military technical document. They don't just recommend adopting grade 104/150. They argue that it should be implemented immediately, before any further testing, because the performance advantages are so overwhelming that further delay would be operationally negligent. Think about what that means. Military procurement normally moves at glacial speed. New equipment goes through years of testing, evaluation, field trials, more testing, budget reviews, more testing. The idea that engineers would recommend deploying something after a single series of tests is extraordinary. But the numbers justify the urgency. In January 1944, when these tests are conducted, the air war over, Europe is reaching a critical point. The 8th Air Force is losing bombers at unsustainable rates. Fighter escorts are stretched to their operational limits. Luftwaffe pilots are getting better at exploiting the weaknesses in American tactics. 20 miles per hour doesn't sound like much. It's the difference between running a mile in 7 minutes versus 6 minutes 50 seconds. But in air combat, that 20 miles per hour is the difference between catching an enemy fighter before it escapes to cloud cover and watching it get away. It's the difference between having enough speed to disengage from a bad situation and being forced to fight when the odds are against you. 500 feet per minute in climb rate is the difference between reaching bomber altitude before the enemy fighters do and arriving late to find the bombers already under attack. It's the difference between having energy advantage in a dogfight and being the one fighting uphill. These margins matter. They matter in ways that are difficult to quantify in peacetime, but become brutally obvious when people are shooting at you. By March 1944, The Army Air Forces makes the decision. Grade 104/150, designated more commonly as 100/150 fuel, will be issued to selected fighter squadrons for operational evaluation. Not all squadrons. Not yet. The production capacity doesn't exist. But enough squadrons to prove the concept in combat. The Royal Air Force has been running similar tests in Britain. Their results mirror the American findings. Spitfires and Tempests on 150-grade fuel show massive performance improvements. More importantly, they're using that fuel operationally against German Wohn flying bombs, the buzz bombs that Hitler is launching at London. The Wohn is fast, 390 miles per hour in level flight, powered by a pulse jet that sounds like a demonic motorcycle. Standard Spitfire Mark 9s and Hawker Tempests struggle to catch them, especially if the Wohn has any altitude advantage. But on 150-grade fuel, both aircraft types can overtake the flying bombs reliably. British pilots start calling the fuel Purple Passion because of the dye and because of what it does to their aircraft's performance. American pilots adopt the term. By summer 1944, every fighter pilot in the European theatre knows about the purple fuel. Most of them are desperate to get it. But production is the bottleneck. Making 100/150 fuel requires processes that most refineries don't have. You can't just add more tetraethyl lead to standard 100 octane and call it good. The base stock has to be different. The aromatic compounds have to be precisely balanced. The refining process involves catalytic cracking, alkylation, and polymerization in specific sequences. American petroleum companies, primarily Shell, Standard Oil of New Jersey, Phillips Petroleum, and several ISGZ, others, start building new refining capacity. The investment is enormous, millions of dollars in new equipment, specialized catalysts that have to be imported or manufactured under license, quality control laboratories that can test fuel batches to unprecedented precision. The production ramp-up takes months. In March 1944, American refineries are producing maybe a few thousand gallons per week. By May, it's tens of thousands of gallons. By June, when D-Day launches, production has reached the point where selected fighter groups can be supplied consistently. The 8th Air Force in England gets priority. Specific fighter groups transition to the new fuel in a carefully managed rollout. The aircraft have to be modified slightly. New spark plugs rated for higher combustion temperatures, revised fuel system components that can handle the fuel's chemical composition without degradation. It's not a major overhaul, but it requires maintenance, time, and specialized parts. The operational results start coming in almost immediately. Fighter groups using 100/150 fuel report higher kill ratios, not because the pilots suddenly got better, not because the German pilots suddenly got worse, because the American fighters are faster and can climb better, which translates directly into tactical advantages. A Mustang pilot who spots a Messerschmitt Bf 109 at his altitude can now be confident he can chase it down if it tries to run. Before the fuel upgrade, that wasn't guaranteed. The 109 could often extend away, using its speed advantage to escape. Not anymore. A Thunderbolt pilot engaging Focke-Wulf 190 fighters at 25,000 feet can now outclimb them consistently. The 190 is a formidable aircraft, fast and well-armed, but the P-47 on high-octane fuel has energy advantages that make the fight less even than it used to be. The Luftwaffe notices. German intelligence reports from mid-1944 start mentioning that American fighters seem faster, more aggressive, more capable of sustained high-speed operations. The German analysts can't figure out why at first. The aircraft types haven't changed. The American pilots haven't suddenly gained experience overnight. It takes captured documents and interrogations of shot-down pilots before they realize the Americans have upgraded their fuel. The Germans try to respond. They've been working on their own high-octane fuels, designated C3 and Super C3. By late 1943, they're producing limited quantities of fuel, rated at 96 octane lean mixture, 120 rich mixture. It's good fuel, better than what they started the war with. But it's not 150. And more critically, German production capacity is limited. Their petroleum comes from three sources: imported oil from Romania, which is vulnerable to bombing and eventually gets cut off as Soviet forces advance; synthetic fuel from coal, produced through the Fischer-Tropsch and Burgess processes at enormous industrial plants that are also vulnerable to bombing; and small amounts from other occupied territories. The synthetic fuel plants are marvels of German engineering. They're converting coal into gasoline through chemistry that's years ahead of what anyone else is doing. But the process is inefficient. It takes 7% of the feedstock and converts it to waste gases. German fuel chemists can't afford that loss. They need every drop. So German aviation fuel is produced through processes that prioritize volume over quality. They get decent octane numbers by adding tetraethyl lead to fuel that has aromatic compounds from coal synthesis. But the resulting fuel is inconsistent. It runs rough. It causes higher cylinder temperatures at lean mixture settings. It fouls spark plugs faster than Allied fuel. German pilots know their fuel is inferior. They learn to manage it. They run their engines rich when they can afford the fuel consumption. They replace spark plugs more frequently. They accept that their aircraft won't perform quite to specification because the fuel won't let them. By summer 1944, the fuel disparity is one more advantage the Allies have in a growing list: better production, better logistics, more pilots, more aircraft, and now better fuel-feeding engines that were already competitive with German designs. The combination is devastating. Luftwaffe fighter units that were holding their own in early 1944 start suffering unsustainable losses by autumn. Some of it is attrition. Some of it is the quality of German pilots declining as experienced veterans are killed and replaced with undertrained rookies. But some of it is simply that American fighters on 150-grade fuel are harder to fight and harder to escape from. The fuel also creates problems. The Army Air Forces discovers this quickly. The biggest issue is spark plug life. On standard 100-octane fuel, spark plugs last maybe 50 to 75 flight hours before they need replacement. On 150-grade fuel, running at higher combustion temperatures and dealing with more lead deposits, plugs last maybe 12 to 15 flight hours. That's catastrophic from a maintenance perspective. A fighter squadron flying intensive operations might need to change plugs every 2 or 3 missions. Changing plugs isn't complicated, but it's time-consuming. 8 plugs per cylinder, 12 cylinders in a Merlin engine. That's 96 plugs per aircraft, multiplied by 20 or 30 aircraft in a squadron. The maintenance burden is enormous. Ground crews start working double shifts. The logistics system has to supply spark plugs at rates that strain the procurement system. At one point in late 1944, the 8th Air Force is consuming spark plugs faster than factories can produce them. Units start rationing plug changes. Running. Engines slightly longer than recommended because they don't have replacements. The fuel also attacks rubber components. The aromatic compounds in 150-grade fuel dissolve certain types of synthetic rubber used in fuel lines and gaskets. Aircraft start experiencing fuel leaks from components that were fine with standard fuel. The solution is to replace the rubber parts with components made from fuel-resistant materials. But that requires more parts, more maintenance time, more logistics burden. There's also the toxicity problem. Tetraethyl lead at 4.6 cubic centimeters per gallon means every gallon of fuel contains nearly 3 grams of lead. Ground crews handling this fuel day after day start showing symptoms of lead poisoning: headaches, nausea, tremors, memory problems. The Army issues safety protocols. Crews are supposed to wear gloves. They're supposed to work in well-ventilated areas. They're supposed to limit their exposure time. In practice, this doesn't always happen. Ground crews in forward areas are working in temporary facilities with inadequate ventilation. They're working urgently, trying to get fighters back in the air as quickly as possible. Sometimes they skip the safety precautions because they don't have time. Some ground crew members get seriously ill. The Army tries to rotate personnel more frequently to limit exposure. They issue better protective equipment. But the fundamental problem remains. The fuel is poison, and there's no way to make it not poison while maintaining its performance characteristics. Despite all these problems, the Army keeps using the fuel. Because the operational advantages outweigh the maintenance headaches and health risks. Fighter pilots aren't complaining about the maintenance burden. They're not complaining about spark plug changes. They're getting better performance, which means better survival rates, which means more of them come home. That's the calculation. More maintenance work. Health, risks for ground crews. Supply chain problems with consumables. All of that is acceptable, because the alternative is sending pilots into combat with aircraft that are slower and less capable than they could be. By D-Day, June 6, 1944, 100/150 fuel has become the standard for fighter units in the European theatre. Not all units. Production still can't keep up with total demand, but the priority units, the ones doing bomber escort and air superiority missions, get the fuel consistently. The 9th Air Force, supporting ground operations in France, takes longer to transition. Their fighter bombers are doing different missions: close air support, ground attack, interdiction strikes against transportation targets. For these missions, the performance advantages of high-octane fuel are less critical than they are for high-altitude air combat. So the 9th keeps using 100 octane for longer. They don't transition to 150 until late 1944, after production has ramped up enough to supply everyone. That's pragmatic logistics. Put the limited high-octane fuel where it has the most impact. The Pacific Theatre gets the fuel even later. Part of this is distance. The production facilities are in the United States and the Caribbean. Getting fuel to Europe means shipping across the Atlantic to Britain, a well-established route with good port facilities. Getting fuel to the Pacific means shipping thousands of miles to forward bases on islands that might not have proper storage facilities. Part of it is also priority. The air war in Europe is considered more critical in 1944. Germany is the primary threat. Japan, while still dangerous, is clearly losing. The strategic priority is to finish Germany first, then focus everything on Japan. So Pacific-based fighter units keep running 100 octane longer. They don't get 150 grade in quantity until early 1945, when the war in Europe is winding down and production capacity has increased enough to supply multiple theatres simultaneously. But when they do get it, the results mirror what happened in Europe. P-38s escorting B-29s over Japan suddenly have more speed and climb rate. P-51s flying from Iwo Jima to attack targets in the Japanese homeland can operate at higher power settings, giving them more tactical flexibility. The Japanese air forces never develop equivalent fuel. Their highest octane aviation gasoline tops out around 91. They try. They invest in refining capacity. They attempt to synthesize high-octane fuels from the petroleum resources they control in the Dutch East Indies and elsewhere. But they're working from a smaller industrial base. They have less access to tetraethyl lead. Their refining technology is years behind American and British capabilities. And by 1944, they're also getting bombed constantly, which makes maintaining any kind of sophisticated industrial production nearly impossible. Japanese fighter pilots know they're outmatched. Not just in numbers, not just in pilot training, but in the basic performance of their aircraft. A Mitsubishi, a 6M0 that was competitive in 1942, is obsolete by 1944. Newer Japanese fighters like the Kawanishi N-1K Shiden and the Mitsubishi J-2M Raiden are better, but they're still running on inferior fuel, which limits their engine performance. The fuel gap compounds every other advantage the Allies have. It's not the most visible advantage. It's not as obvious as having more aircraft or more pilots, but it's fundamental. It affects every mission, every engagement, every tactical decision. A fuel advantage doesn't guarantee victory in any individual dogfight. Pilot skill still matters. Aircraft positioning still matters. Luck still matters. But across thousands of engagements, small performance advantages accumulate into statistical dominance. If your fighter is 5% faster and your opponent is 5% slower, and this happens in 100 fights, you're going to win more than you lose. By the end of 1944, the Allied air forces have achieved something close to air superiority over Europe. Multiple factors contribute to this. German pilot quality declining, Allied numerical superiority, better tactics, better intelligence. long-range fighter escorts enabling bomber streams to penetrate deep into Germany. But fuel is part of the equation. 150-grade fuel gives Allied fighters performance advantages that make every other advantage more effective. It's a force multiplier, not the only one, but a significant one. The story doesn't end in 1945. High-octane aviation fuel continues to evolve after World War II. The military develops grades with even higher performance numbers. 115/145 fuel becomes standard for piston-engined military aircraft in the late 1940s and early 1950s. The United States Air Force flies piston-engined attack aircraft well into the 1970s. Douglas Aoni Sky Raiders in Vietnam, powered by Wright R-3350 radial engines, burning 115/145 fuel, the same basic chemistry that powered Mustangs over Berlin in 1944, refined and improved, keeping older aircraft competitive in a jet age. The Navy operates training aircraft with piston engines until 1984, North American 28 Trojans, with Pratt & Whitney R-1820 radials, running on high-octane fuel that traces its lineage directly back to Doolittle's experiments in the 1930s. And if you've ever been to an air show and smelled the exhaust from a warbird doing a flight demonstration, that distinctive sweet smell that hangs in the air long after the aircraft passes, that's the aromatics in high-octane aviation fuel. That's the same fuel chemistry, the same tetraethyl lead, the same compounds that gave Allied fighters their edge in World War II. Today, general aviation still uses leaded fuel. 100 low lead, designated 100 LL, contains tetraethyl lead at lower concentrations than wartime fuel, but still enough to prevent detonation in high-compression piston engines. It's the last remaining use of leaded gasoline in most countries, maintained because no economically viable replacement exists for the thousands of piston engine aircraft still flying. There's ongoing work to develop unleaded aviation fuel. Multiple companies and research groups are testing alternatives. The Federal Aviation Administration approved the first commercially produced unleaded aviation fuel in 2021, but the transition is slow, complicated by the need for fuel that works in engines designed decades ago, some of them dating back to designs from the 1940s and 50s. The story of 150-octane fuel is ultimately a story about the invisible advantages that determine outcomes. You can't see octane rating. You can't touch it. When you look at a P-51 Mustang sitting on a runway, there's nothing visual that tells you whether it's running 100-octane or 150-octane fuel. But that invisible difference changes everything. It changes how fast the aircraft can fly, how quickly it can climb, how much power the pilot can call on when he needs it. And in combat, those differences translate directly into survival. The engineers who developed this fuel weren't glamorous figures. They didn't lead bomber raids. They didn't shoot down enemy fighters. They worked in refineries and laboratories, dealing with toxic chemicals and complex industrial processes. Most of them never got famous. Most of their names don't appear in history books. But their work gave Allied pilots advantages that accumulated mission after mission into air, superiority, into the ability to escort bombers deep into enemy territory, into the ability to intercept enemy aircraft consistently, into the ability to dominate the skies over Europe by 1945. Jimmy Doolittle is remembered primarily for the Tokyo raid in April 1942. 16 B-25 bombers launched from the carrier USS Hornet to attack Japan, proving that the Japanese homeland was vulnerable. It was a brilliant psychological operation, and it earned Doolittle the Medal of Honor. But some historians argue that Doolittle's greatest contribution to the war effort came years earlier, when he was a civilian working for Shell Oil, convincing executives to invest in refining capacity that nobody needed for aircraft that didn't exist yet. When he was lobbying the Army to adopt fuel specifications that would require massive changes to logistics and maintenance systems. That wasn't glamorous. It didn't make newspaper headlines. It was bureaucratic trench warfare, fought in conference rooms and procurement offices, armed with charts and test data instead of bombs and guns. But it created the foundation for air superiority that would prove decisive. The chicken and egg problem Doolittle identified in the early 1930s was real. Engine manufacturers wouldn't design high-compression engines without high-octane fuel. Oil companies wouldn't produce high-octane fuel without engines that needed it. Both sides were waiting for the other to move first, and neither had an incentive to take the risk. Doolittle broke the deadlock by using his fame and technical credibility to force both sides to move simultaneously. He got Shell to invest in refining capacity by demonstrating performance gains in air races that generated publicity. He got the Army to adopt new fuel standards by presenting data showing that American aviation was falling behind European developments. He created the market and the demand at the same time. And he did it before the war started, which meant the industrial capacity existed when it was needed. If the United States had waited until 1942 to start building high-octane refining capacity, the war would have looked very different. The Battle of Britain happens in July through October 1940. If the RAF hadn't had 100-octane fuel stockpiled and ready to use, British fighters would have been slower than German fighters. The tactical situation might have been untenable. Britain might have lost air superiority, which would have made invasion possible. The strategic bombing campaign over Germany accelerates in 1943 and 44. Without long-range fighter escorts enabled by high-octane fuel, bomber losses would have been unsustainable. The campaign might have been abandoned or radically curtailed. These are counterfactuals, and counterfactual history is always speculative. But the basic logic is sound. Air superiority was decisive in World War II. Fuel octane was a significant factor in achieving air superiority. Therefore, fuel octane was a significant factor in the war's outcome. The invisible advantage, the one that doesn't show up in photographs or newsreels, the one that required years of development before the war and continuous production throughout the war, and caused enormous logistical and maintenance challenges, but delivered performance gains that accumulated into dominance. There's a broader lesson here about technology and warfare. The most decisive technologies aren't always the most visible. Radar won the Battle of Britain as much as Spitfires did, but radar isn't photogenic. Logistics won the war in Europe as much as tanks and infantry did, but supply chains don't make compelling narratives. Fuel octane is another example. Critical importance, minimal visibility. The kind of thing that only becomes obvious when you dig into the technical details and realize how much performance was sitting on the edge of detonation, held back by fuel chemistry. The engineers and chemists who pushed octane ratings from 87 to 100 to 150 over the course of 15 years weren't thinking about historical impact. They were solving immediate technical problems. How do you prevent engine knock? How do you extract more power from a given displacement? How do you make fuel that doesn't poison everyone who handles it while still delivering anti-knock properties? They solved these problems incrementally, through trial and error, through industrial chemistry that required massive capital investment and sophisticated quality control. And the cumulative result of their work was that Allied fighters in 1944 could fly faster and climb better than Axis fighters using less advanced fuel. 20 miles per hour. 500 feet per minute of climb rate. These are the margins that matter. Not huge, not overwhelming, but consistent, reliable, present in every engagement, every mission, every tactical situation. A Mustang pilot over Germany in late 1944, running on 150 grade fuel, has options that his predecessors in 1943 didn't have. He can chase down enemy fighters that try to escape. He can climb to intercept threats at higher altitudes. He can extend away from dangerous situations using speed advantage. These options change tactics. They change what's possible. They change outcomes. And they exist because chemists and engineers spent years figuring out how to blend aromatic compounds with tetraethyl lead in precise ratios that would burn in cylinders without detonating prematurely. The P-51 Mustang is often called the best fighter of World War II. That's debatable, and every fighter has advocates who will argue for their preferred aircraft. But the Mustang's reputation rests on several factors working together. Good airframe design, excellent engine, long range from internal fuel capacity, and the ability to use high-octane fuel effectively. Take away the 150 grade fuel, and the Mustang is still a good fighter. but it loses the performance edge that made it dominant. It's slower. It climbs slower. It can't maintain high power settings as long. The tactical advantages that made Mustang units so effective start to evaporate. This is what makes fuel such a critical technology. It's not additive. It's multiplicative. A good aircraft design with bad fuel is mediocre. A good aircraft design with good fuel is exceptional. The aircraft doesn't change. The pilot doesn't change. But the performance envelope expands, and that expansion creates opportunities that didn't exist before. The Luftwaffe learned this lesson the hard way. German fighter designs in 1944 and 45 were often excellent. The Focke-Wulf 190 Dora 9, the Messerschmitt Bf 109 K4, the Focke-Wulf TAR 152. These were sophisticated aircraft with good aerodynamics and powerful engines. But they were running on fuel that couldn't fully utilize their potential. German pilots knew they were giving up performance because of fuel limitations. They learned to work around it. They developed tactics that minimized exposure to extended high-power operations. They conserved fuel by running lean mixtures whenever possible. But tactics can only compensate so much for a technical disadvantage. If your opponent's fighter can run at full power longer without detonation problems, and can achieve higher maximum speeds, and can climb faster, you're fighting uphill every engagement. Skill can overcome that in individual cases. But across hundreds of engagements, the side with the performance advantage wins more often. By April 1945, the Luftwaffe is effectively finished as a fighting force. They still have aircraft. They still have pilots, though most are barely trained. But they can't contest Allied air superiority. American and British fighters operate over Germany with near impunity. Multiple factors contribute to this collapse: attrition, fuel shortages, pilot training failures, strategic bombing of German industry. But part of the story is that Allied fighters have performance advantages from better fuel, and those advantages compound every other Allied strength. The war in Europe ends in May 1945. The war in the Pacific ends in August, after atomic bombs are dropped on Hiroshima and Nagasaki. Piston-engined fighters are about to become obsolete, replaced by jets that don't use octane-rated fuel at all. But for the 3 years between mid-1942 and mid-1945, high-octane aviation fuel was one of the decisive technologies of the war. Not the only one, not even the most important one, but significant enough that its absence would have changed outcomes. The engineers who developed this fuel went back to peacetime work. The refineries kept producing, transitioning to commercial aviation and military aircraft that still used piston engines. The chemistry they developed remained relevant for decades, until jets replaced pistons as the primary military aircraft type. Jimmy Doolittle retired from the Air Force in 1959 as a lieutenant general. He remained active in technical fields, serving on corporate boards and advisory committees. He died in 1993, at age 96, having lived long enough to see most of his contributions to aviation become historical footnotes. But his legacy is embedded in every high-octane fuel formulation still in use today. The basic principles he fought for in the 1930s, that fuel is a performance-critical system and deserves the same engineering attention as airframes and engines, became foundational to aviation development. The question of whether one mechanic's stupid 150-octane mix let P-51s outrun every Luftwaffe fighter is, in some ways, the wrong question. Because it wasn't one mechanic. It was Jimmy Doolittle, a pilot with a doctorate in aeronautical engineering. It was dozens of petroleum engineers and chemists at Shell, Standard Oil, Phillips, and other companies. It was the Army Air Force's Material Command engineers who tested the fuel and wrote reports demanding immediate deployment. It was the ground crews who dealt with the maintenance, headaches, and health risks. It was the pilots who flew combat missions and came home because their aircraft were faster than the enemy's. It was a systemic effort, spread across years, involving thousands of people working on unglamorous problems that most people never think about. And the result was that Allied fighters in World War II had invisible advantages that accumulated into dominance. The fuel was purple, the performance gains were real, and the war in the air was won, in part, by chemistry that happened before the spark plug fired. Thank you for watching. For more detailed, historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.